Second part of section 1 expands the idea of similarity beyond just lengths. Now we're going to talk about the area of similar figures. Now, just to kind of motivate this a little bit more, if I have, say, let's take a very simple figure, a square. And this square has sides 3. Okay, perfect square, sides 3. The area of that square is 3 times 3 or 9, let's say meters, so 9 meters squared, right? What if I get a square that has sides twice as long? So a square with sides 6, that might be more than twice, but that's okay, you get the idea. Now, we know that the perimeter of this square right here, okay, in fact, I'll do this in a different color in a second. We know the perimeter of this square, by the way. Can't use my tools properly. Here we go. The perimeter is 3, 6, 9, 12, or 12 meters. Okay? Since this is twice as long, I know the perimeter is also twice as much, so the perimeter of that square has to be 24 meters. And when I think about that, 6 plus 6 plus 6 plus 6 is indeed 24. The question is the area twice as much as the area of the first one? The area of the first square was 9 meters, but the area of this is not 18 meters. It's very clearly 36 meters squared. 6 times 6 is 36. So what gives? Why are all these scale factors and ratios, everything's 2 to 1, 2 to 1, 2 to 1, and we get the areas and suddenly it's not 2 to 1, it's 4 to 1. Why is that the case? Well, that's what we're going to talk about today, the corresponding areas. And quite honestly, the corresponding areas, when we do that, the ratio of the areas is the square of the scale factor. Why is it the square? Because how do we find area? Let's go back here. How did I find the area of this square? I multiplied a length times a width, right? I multiplied. So I didn't add the units like I did when I found the perimeter. Perimeter was added. The units stayed the same. I mean, everything was in meters. The perimeter is still meters. It's still a length. But when I find area, I have to multiply lengths. So my units change. From 6 meters, it's 36. 6 times 6 is 36. Meters times meters is meters squared. And so I've changed my units, which means my scale factor also has to change by that same rate. So even though the ratio is meters to meters, for lengths, the ratio for this is meters squared to meters squared. So bottom line is, and this is kind of a big thing, but if the scale factor, which applies to all lengths, is A to B, then the ratio of areas is A squared to B squared. And it has to do with the units, because it's measured in units squared. Guess what? Ratio of volumes is going to be A cubed to B cubed. We'll get there, I think, in chapter 12. But it's the same basic idea, because volume is measured in units cubed. So pretty simply put, here I have 2 triangles. The area of the first triangle we're given is 36 centimeters squared. The area of the second triangle we need to find. In order to do that, we're going to have to set up a proportion. But we're going to have to find the ratio of areas in order to do that. This is your problem, but I'm going to get you started. The scale factor, and I'm just going to move left to right like we normally do as we read. The scale factor is clearly 10 over 5, which reduces to 2 over 1. We always want to reduce that. So what is my ratio of areas going to be? Okay. What is my ratio of areas going to be? In fact, that's where I'm going to have you answer the question. Now that we've got the ratio of areas, let's find the corresponding area. So my ratio of areas was 4 to 1. And my areas are 36 and unknown. big to small, big to small. And that's a pretty easy cross-multiplying. 4x equals 36, so x equals 9, or similar fraction, either way, x equals 9 centimeters squared. Okay? That's the area of my smaller triangle. One more time. Here are my ratio of sides. I'm given the area of GHJK, which is the smaller one. This is 84 meters squared. Find the area of this one. This one you're doing entirely on your own. Next, decide whether these two shapes are similar. Explain your reasoning. Now, this is a little trickier than it might look, because we do have to go ahead and take into consideration certain things. But let's go ahead and just start looking at how we do this. First off, I don't know if all the corresponding angles are the same, but I do know angle A corresponds to angle K. That's marked. Okay? So now we have to work our way around. Corresponding sides. The 12 either goes with this 8 or that 8. I'm not sure, but they're both 8s, so I'm pretty safe that way. So I'm going to go longer to shorter, 12 over 8, and reduce that fraction. 4 goes into both of that. That's 3 over 2. So this 12 going with that 8. Next, we'll go with this 9 and this 6, because those are the next ones going around. 9 over 6 reduces to 3 over 2. So far, so good. Next, we go to the next sides around. 6 over 4. That reduces to 3 over 2. Gosh, so far so good. 9 and 6. 9 over 6 reduces to 3 over 2. And finally, 12 and 8. All the corresponding sides reduce to 3 over 2. They all reduce to the same thing. Are those figures similar? Yes. Okay? If all the corresponding sides reduce to the same scale factor, we should have similar figures in most cases. Now, is that absolute proof? Well, no. That's not proof. We don't have a theorem that says that's true. In fact, I can tell you that's not always true. Take, for example, if I have a square and I have a rhombus. And all the sides here are 5. And all the sides here are 3. If I take this corresponding sides, it's always going to be this ratio of 5 to 3, isn't it? But are they similar figures? No. So just having the same scale factor all the time doesn't guarantee it's going to be similar. However, when I throw in all the sides plus a corresponding angle, we're getting closer to the idea of proving that two things are similar. We're going to spend a lot of time dealing with that concept in the future. Okay? Are the hexagons in tile design 1 similar? Are the hexagons in tile design 2 similar? Okay? In tile design 1, it's clear that the corresponding sides, all the angles are congruent in the red hexagon. Clearly, the angles are not indicated as all congruent in the blue one. All the sides are congruent in the red hexagon. Not all the sides are congruent in the blue one, so these are not similar. In the second design, all the sides in the red hexagon are congruent, all the angles in the red hexagon are congruent. Same with the blue, just smaller. So if like all these sides are 8 and all these sides are 7s, yeah, obviously this is going to be similar polygons. So this is yes. All corresponding sides proportional, all corresponding angles are congruent. So again, more dealing with the similarity, but again, focus on this idea of the ratios of areas. We're going to talk more about proving things similar in future sections. We'll really get into that a lot with triangles, but corresponding areas are kind of the big deal for now. All right, we'll see you in class.